Hello students, welcome back to Learn 24. In this video, we are going to learn about the factors which are influencing the rate of a chemical reaction, and also we are going to learn about the Arrhenius equation. First, let's learn what are the factors which are influencing the rate of a chemical reaction. The most important one is the concentration of reactants. Rate increases with the increase in concentration. As the concentration of reactant is increasing, the rate or the speed of chemical reaction also increases. Higher the concentration of this reacting species will lead to the more collision between these reacting species with the instant of time. So, there increases the speed of a chemical reaction. That is, rate is directly proportional to the concentration of reactants. Always remember, rate of a chemical reaction increases with the increase in the concentration of reacting species. The next one is the nature of reactants. There are many kinds of reactants, and one of them is the ionic reactants. For example, NaCl plus AgNO3 will give AgCl and NaNO3. All of them are in the ionic state, that is Na plus Cl minus, Ag plus and NO3 minus, Ag plus and Cl minus, Na plus and NO3 minus. All of them are in the free state. Hence, the rate or the speed of chemical reaction also increases. If the chemical reaction containing the ionic reactants, rate of a chemical reaction increases. The next one is the covalent reactants. For example, N2 plus 3H2 will give 2NH3. That is, there is a triple bond between these two nitrogen. 3 covalent bonds between nitrogen, and between hydrogen there is one covalent bond, and between nitrogen and hydrogen there is also the covalent bonds. So, in order to break these bonds and also to form new bonds, they require more time and more energy. Hence, if the reaction containing the covalent reactants, the rate or the speed of chemical reaction is decreases. If the chemical reaction having covalent reactants, rate of a chemical reaction decreases. Now, also we have homogeneous reactants and a heterogeneous reactants. If we have same kind of reactants, it is called a homogeneous reactant. If we have different kind of reacting species, that is called the heterogeneous reactants. And the rate of reaction is increases with the homogeneous reactants. If the chemical reaction having homogeneous reactant, rate of a chemical reaction increases than the heterogeneous reactants. Now, the next factor will be the physical state of reactants. So, the rate increases if the reacting species are in gaseous state, because in gaseous state the molecules are in free state, right? So, they can move around and they can collide with each other. So, the chemical reaction, the speed of chemical reaction also increases. And in solid state they are compactly arranged, right? They are compactly arranged. So, the chances of collision is less in the solid state than the gaseous state. So, the rate of a chemical reaction is, order for the rate of chemical reaction is gas is greater than liquid is greater than solid. So, the rate of chemical reaction increases if the reactants are in gaseous state. And the next one is the size of reactants. Rate of a reaction is directly proportional to the surface area of reactants. Let me give you an example. I have 2 glasses of water. In one of them, I have added powdered sugar, and the other one, I have added the sugar crystals. Which one will dissolve faster? Definitely, the powdered sugar will dissolve faster than the sugar crystals. Yes, the rate of a chemical reaction depends on the size of reacting species. That is, as the size decreases, the rate of a chemical reaction increases. As the size decreases, rate of a chemical reaction or the speed of a chemical reaction also increases. Clear? The next factor will be the catalyst. As we already know, on adding the catalyst, they increases the speed of a chemical reaction. So by adding this catalyst, it increases the rate of a chemical reaction. For example, I have 2 KClO3 which will give 2 KCl and 3O2. By adding a catalyst MnO2, it will speed up the reaction. So the rate of a chemical reaction increases while adding the catalyst. Let me show you with a graph. On y-axis, I have took the potential energy, and on x-axis, I have reaction coordinates. So before that, you have to know a term called the activation energy. Activation energy is the minimum amount of energy that is required by the reactants in order to convert into the product with a particular time period. So the reacting species must have a small amount of energy to convert into the product, and that energy is called the activation energy. So the reactant over here should convert into the product, and they require a minimum energy called the activation energy. So this will be the activation energy of these reacting molecules. They require this much activation energy to carry out this chemical reaction. Now, if I am adding a catalyst to this chemical reaction, they speed up this chemical reaction by decreasing this activation energy. This is the path. If I add the catalyst, they decreased the activation energy this much. So the reactant now should have only this much energy to convert into the product. They increases the speed of a chemical reaction. Clear? Now the next important factor called the temperature. As the temperature increases, rate also increases. Rate of reaction increases with the increase in the temperature. If I am increasing the temperature of a chemical reaction, the collision will be more because the molecule will acquire more kinetic energy. They will move faster, so the chances of collision is more. Hence, the chemical reaction speed is also increases. Rate of a chemical reaction increases with the increase in temperature. Now I have a general equation. AA plus BB will give CC and DD. Also, I can write it as rate is directly proportional to the concentration of A power X into concentration of B power Y. The exponents X and Y may or may not be equal to A and B. Here X and Y are the experimental values. Here A and B are the theoretical values. May or may not be equal to A and B. Now, in order to remove this proportionality sign, I am adding a constant K, and it is called the rate constant. In order to remove this proportionality sign, I am adding a constant called the rate constant, and this expression is called the rate expression or the rate law. So the rate law is rate is equal to K, rate constant, into the concentration of A power X into concentration of B power Y. Also, I can write it as minus the concentration of R divided by dt, and that will be equal to rate constant into concentration of A power X into concentration of B power Y. Now you have to remember two terms, order and molecularity. What is order? Order is the sum of powers of concentration of reactant species in the rate expression or the rate law. So here X plus Y will give you the order of the reaction. X plus Y will give you the order of the chemical reaction. Clear? Yes, it is the sum of powers of the reacting species in the rate expression or the rate law. It is an experimental value. Always remember, it is an experimental value. Now what will be the molecularity now? Molecularity is the number of reacting species. which must collide simultaneously in order to bring about a chemical reaction. There are A and B molecules. So A plus B will give you the molecularity of those chemical reaction. It is a number of reacting species which must collide to bring about a chemical reaction. So A plus B will give you the molecularity, which is a theoretical value. X plus Y will give you the order of a chemical reaction. Now, the molecularity cannot be 0, but the order can be 0 or fractional. Clear? Yes. Now let me give you an example for the molecularity. I have a chemical reaction. H2O2 will give H2 plus O2. The number of reacting species here is 1, right? Yes. So the molecularity is also 1. Hence this reaction is a unimolecular reaction. This reaction is a unimolecular reaction. Now I have 2HI will give H2 plus I2. Here the number of reacting species is 2. Hence this is a bimolecular reaction. It is a bimolecular reaction since the two molecules are taking place in this chemical reaction. Now I have 2NO plus O2 will give 2NO2. The number of reacting species here is 2 plus 1, right? It is 3. Hence, it is a trimolecular reaction. It is a trimolecular reaction. Clear with the unimolecular, bimolecular and trimolecular reactions? Yes. The next, for example, I have again 2NO plus O2 will give 2NO2. I can give the rate is equal to K into concentration of Na power 2 into concentration of O2, right? The rate equation was rate is equal to K into concentration of A power X into concentration of B power Y. So A here is NO and X is 2 and B is O2 and Y will be 1. So X plus Y will give you the order of the reaction. So 2 plus 1 is 3. So it is a third order reaction. And the molecularity here is 2 plus 1. It is a trimolecular reaction. And also I can write it as minus the concentration of R divided by dt gives K into concentration of Na power 2 into concentration of O2. Now, as I told you, rate is equal to K into concentration of A power Y into B power Y. So, the X plus Y will give you N. It is the order of reaction as we always know. And also I can write it as K is equal to rate divided by concentration of A power X into concentration of B power Y. In general, I can write it as K is equal to rate divided by concentration of R power N. N will be the order of reaction. Now we have to determine the unit of these chemical reactions. So if the order changes, the units also changes. Now let's learn about the unit for the zero order chemical reaction. So put the order as 0 over here. And what was the unit for rate? Do you remember the unit of rate? It is the mole liter inverse second inverse, right? The unit of mole was mole liter inverse second inverse. It is divided by the concentration. So the unit of concentration is mole liter inverse power N is 0, right? So the concentration power 0 will give 1. So the unit of zero order reaction will be mole liter inverse second inverse. Always remember, the unit for a zero order chemical reaction is mole liter inverse second inverse. Now for the first order chemical reaction, the unit of rate is mole liter inverse second inverse divided by the concentration. Unit of concentration is mole liter inverse power 1, because we are determining the unit for the first order chemical reaction, power 1. So this will be mole letter inverse, and mole letter inverse will get cancelled, and the remaining thing is second inverse. So the unit for the first order chemical reaction will be second inverse. Always remember, the unit for first order chemical reaction is second inverse. Now we have to determine the unit for the second order chemical reaction. The unit for the rate was mole liter inverse second inverse divided by the unit of concentration was mole liter inverse power 2, because we are determining the unit for the second order chemical reaction. Now I can also write it as mole liter inverse second inverse divided by mole square liter raised to minus 2, right? Yes. Now the mole over here and mole get cancelled. L raised to minus 1 and L raised to minus 1 will get cancelled. Then the remaining thing is mole inverse, liter inverse and second inverse. This will be the unit for the second order chemical reaction. This is the unit for second order chemical reaction. Mole inverse, liter inverse and second inverse. Now, for a chemical reaction, with a rise in temperature by 10 degrees Celsius, the rate constant is nearly doubled. If I have a chemical reaction and I am increasing the temperature by 10 degrees Celsius, the rate constant K will be doubled. For example, I have a chemical reaction where the rate constant is 2. Rate constant is 2. Now I am increasing the temperature by 10 degrees Celsius. So the rate constant will be doubled, right? Now the rate constant will be 4. Now again I am adding or increasing the temperature by 10 degrees Celsius. Again this rate constant will double. So the rate constant was 4 over here. Again it will double and becomes 8. Clear? Yes. For a chemical reaction with a rise in temperature by 10 degrees Celsius, the rate constant is nearly doubled. It is well explained by Arrhenius equation. Arrhenius equation. Let's learn what is Arrhenius equation. K is the rate constant. K will be equal to A e power Ea by RT. K is the rate constant. A is the Arrhenius factor. A is the exponential and Ea will be the activation energy. R is the universal gas constant and T is the temperature. So remember this equation, K is equal to A e power minus Ea by RT. Now for the simplification, we are taking the natural logarithm of this equation. So it will become ln K is equal to ln A into ln e power Ea by RT. So remember, wherever ln e power x will give you the x. So remember this, ln e power x will give you x. So it is in the form like ln e power minus Ea by RT. So it will give minus Ea by RT. So just substitute this over here. Ln K will give ln A minus Ea by RT. Now taking the log by multiplying it with 2.303. That is, log K will be equal to log A minus Ea divided by 2.303 RT. So always remember this equation. Ln K is equal to ln A minus Ea divided by RT. Now we can determine the activation energy by plotting a graph. Now we have a equation ln K is equal to ln A minus Ea divided by RT, right? Now this is in the form of straight lines equation. What was the equation for straight line? It was y is equal to c plus mx. So y over here is ln K. So I am taking ln K on y axis and the x is 1 by t. So the 1 by t will be on the x axis. M is the slope and slope here is minus Ea by r. Minus Ea by r will be the slope. So it is a negative slope. So we can draw the straight line downwards since it is a negative slope. So draw this straight line downwards and the slope will be minus Ea by r. minus EA by R, and EA will be equal to R into slope. So you can determine the EA by using this slope. Now, what is C? C is the y-intercept, it is ln A. So this will be the y-intercept ln A. Clear with the graph? We can also calculate the activation energy by using the equations. At a T1 temperature, the Arrhenius equation will be ln K1 is equal to minus EA divided by R T1 plus ln A. This will be the equation number 1. And at T2 temperature, the Arrhenius equation will give ln K2 is equal to minus EA divided by R T2 plus ln A. So, the K1 and K2 are the values of rate constant at temperature T1 and T2. These are the two equations. Now, by subtracting this equation number 2 by 1, we will get ln K2 minus ln K1 will give EA divided by RT1 minus EA by RT2. Ln A will get cancelled. Now, the ln K2 minus ln K1 is ln K1 divided by K2. Ln K2 minus ln K1 is ln K1 divided by K2, and EA by R is common over here. Let's take it outside. EA by R into 1 divided by T1 minus 1 divided by T2. Now let's take the logarithm of this equation by multiplying it with the 2.303. Now log K2 divided by K1 will be equal to EA divided by 2.303 into R into 1 divided by T1 minus 1 divided by T2. By cross multiplying this, we'll get T2 minus T1 divided by T1 into T2. So the equation will be log K2 divided by K1 will be equal to EA divided by 2.303 R into T2 minus T1 divided by T1 into T2. By knowing these temperatures and the rate constant, we can calculate the activation energy. Now let's learn more about the activation energy. For that, consider a reaction H2 plus I2 will give 2HI. Now, on reacting this H2 and I2, they forms an intermediate. Soon they will break down and forms 2HI. And this intermediate is called the activated complex C. So the intermediate over here is called the activated complex C. In order to make this activated complex C, they require an energy, and that energy is called the activation energy. Clear about this activation energy? Yes. In order to make this activated complex, they require an energy, and that energy is called the activation energy. Clear? Yes. I hope you are clear with all those concepts, and in the next video we are going to learn about the integrated rate equations. So see you in the next video. Until then, bye bye.